Our final invited talk today is Bill Unruh, professor at the University of British Columbia. So I think we all know him. He has an effect on the detector named after him. And he's going to talk us about the Ligo quantum noise and the quantum nature of macroscopic objects. So go ahead, the floor is yours. I'm going to give you a 5-minute warning.
So incidentally, I'm also at the Texas A&M University as well as University of British Columbia. So to start again, I'm talking about a subject that I'm just working on now, which is the use of LIGO for seeing the quantum nature of macroscopic objects. Let me remind you about LIGO. Here's a sort of sketch of what LIGO looks like. There are 4-kilometer-long arms. There are, there are mirrors. Can you see my cursor, by the way?
Yes, we can see it.
Ah, good. There are mirrors at the ends. These are 40-kilogram mirrors. And they have about a megawatt of power sitting inside, bouncing back and forth between these mirrors and the test masses. And out of the output port, you have milliwatts of radiation. So only a tiny, tiny fraction of the actual energy comes out of the output port. You're almost on the dark fringe of the output of this detector. These are 40-kilogram objects. Are they quantum? And can one use the experiments of LIGO to, in fact, argue that they are quantum? And that's what I'm going to do in this talk. If we look at the noise budget of LIGO, this is a plot of the noise budget of LIGO, and look at in particular, the purple curve, which is the important one. That's basically the quantum noise, the quantum vacuum noise. At high frequencies, this is shot noise, i.e. the outcoming signal is riding on a background intensity, as I said, milliwatt intensity coming out the output port. And one is detecting the photons. And of course, these photons come in little lumps and they come at random times. And so you get shot noise on the output, which limits the frequency there. You also have at low frequencies, radiation pressure noise. That's noise which comes about because basically the shot noise pushing on the mirrors pushes them back and forth. It turns out that these two forms of noise are complementary in Bohr sense, i.e. they don't commute with each other. And as a result, at first glance, one would say that if one improves the shot noise, one will always make the radiation pressure noise worse. If one improves the radiation pressure noise, one will make the shot noise worse. That turns out not to be right. So what are these? The radiation pressure noise is basically noise which comes about for the following reason. One has a laser field coming in here, that's in the red. And one has also at the same time vacuum fluctuations, i.e. one has nothing coming into this output port except for vacuum fluctuations. And some of these vacuum fluctuations are in phase with the laser noise. They, of course, increase and decrease the amplitude of the laser noise in both arms. It's of opposite phase in the two arms because of the way in which this mirror operates. But that increases and decreases the intensity of the light going towards the mirrors, and increases and decreases the force on the mirrors due to this light traveling down towards the mirrors. There's also other kind of noise that comes in from that output port, and that is noise which is out of phase with these with the with the oscillations of the laser beam. Remember, the laser beam is up at the megawatt level, and these things are down at the nanowatt level. The vacuum fluctuations are much, much, much smaller. But still, that produces eventually the shot noise that you see at the output. And because they're complementary, we basically have an uncertainty relationship between them. Carl Caves in 1980 showed that the noise in the interferometer arises not from the laser, which is extremely important, because lasers are always rather noisy things. Even the best lasers, which these guys use, always have excess noise. They are not coherent states, as you often hear tell about lasers. They're noisier than coherent states. However, because of the structure of the interferometer, as I'm going to show, excuse my annoyance at my computer. Because of the interference, because of the operation of the mirror and the fact that you're operating basically at the dark fringe of the one, those fluctuations and the very high intensity of the laser itself simply go back out the input port, and you don't see them in the output, which is very fortunate. In 1983, I argued that, in fact, one could do better than this for these laser interferometers. One could, in fact, basically cancel both the shot noise and the radiation pressure noise, or at least the part that gives you the noise in the output reading at the same time. And what effectively happens is that the mirror acts like an amplifier and produces a squeeze state. So let's have a look at the mirror. The radiation coming into the mirror is going to reflect off of the mirror. And basically what the mirror does is produce a phase shift in the light that is coming into the mirror. So psi naught is the incoming beam. Then the outcoming beam, if we assume that the boundary condition on the mirror is zero field, i.e. psi equals 0 on the surface of the mirror, then the output is just equal to the input. But if x, the location of the mirror, is not at 0, then the phase of the output is changed by an amount twice x. In everything I do, I'm going to assume that x is extremely small, which it is in the actual LIGO, something like 10 to the minus 15 of the, or 10 to the minus 18 of the, of 2 pi is the kinds of phase shift that the motion of the mirror gives you. But what this means is that the position of the mirror is imprinted on the outgoing beam because of this phase shifting of the light. If one looks, there are 4 different regions. If we look back in here, we have one region where stuff comes in. We have the laser beam coming in here with its carrying its vacuum fluctuations. One has the vacuum fluctuations coming in the output port. They are mixed via the beam splitter. One then has beams which travel in these 2 arms. And I'm simplifying LIGO by having just a single mirror, a single 2-sided mirror with these 2 beams shining on the opposite sides of that single mirror. LIGO is slightly more complicated, but the essential physics is basically the same. And these beams reflect off and then are recombined when they come back out. So this is the original one. One has a coherent state with amplitude alpha, which is very, very large, plus the vacuum, plus the annihilation operators associated with the electromagnetic field coming into the input port, into the Y direction input port. Remember that X and Y are defined this is y. This beam, this path is called the y and is measured by the variable y, and this beam is x, measured by the variable x. And the beam splitter mixes stuff coming from y, in from y, and in from x. And that looks like this. This is the incoming beam before the beam splitter. After the beam splitter, I'm just assuming a very simple model of the beam splitter, where going out the y direction, one gets an equal mixture of the A's and B's. Alpha gets distributed between the two, and there's a plus sign that disappeared somewhere in my tech. So that's alpha plus. A minus B goes up the x direction, and A plus B goes out in the y direction. It hits the mirror and then gets gets phase shifted via amount x, bouncing back, goes through the mirror again, gets remixed. And the important thing is, what I want to look at is only the stuff coming out of the y port, actually out of the x port. So these should be x's in here. These should be x's in here. And only a tiny bit of the coherent state comes through an amount epsilon, which is some factor like 10 to the minus 15 or 10 to the minus 8 or something, comes out. Similarly, the A fluctuations also get damped out by that same amount. So that means that the noise in the interferometer doesn't come out the output port, which is one of the main reasons why one is operating very near the dark fringe of the interferometer, to reduce the effect of the common mode effect of the laser fluctuations. B comes out virtually undisturbed. It's 1 minus epsilon squared, but since epsilon is so small, I'll just approximate that by B. They come out undisturbed out of the output port. And it's these B vacuum fluctuations that mix with alpha to give you the shot noise, if you will. So X is much, much less than epsilon over omega. So even the fluctuations in the output port are very small. Similarly, I'm going to assume that the fluctuations B are also much smaller than epsilon times alpha. So the amount of B coming out that port is much smaller than the coherent state coming out of that port. Incidentally, what was I going to say? I've forgotten it. Oh, yes. Nu here is the difference in frequency between the frequency of the laser and the frequencies of these annihilation operators. So nu, both for plus nu and minus nu, are both annihilation operators. They're just the annihilation operators on either side by a factor of about 100 hertz on either side of the omega 0, which is about 10 to the 15 hertz. So nu is very, very, very small compared to omega. That allows me to neglect the nu in the normalization factor of the modes. This should actually be 2 pi omega naught plus nu, but nu is so much smaller than omega naught that I can just throw it out. Now, the mirror moves because of two different things. One is the external classical force on the mirror, the gravity wave that comes in. Gravity waves are highly classical. They have of the order of 10 to the 20 gravitons per cubic wavelength. So they behave as just classical forces, if you will. And the noise due to the quantum fluctuations in A and B are also things that move the mirror. Notice, however, that the force due to alpha, alpha is the coherent state, you've got the radiation pressure noise due to alpha, but you get the same amplitude hitting both sides of the mirror. And that same amplitude cancels out on the two sides of the mirror. And so they don't move the mirror at all. The radiation pressure noise is then due to cross terms between the alpha and the A and the B vacuum fluctuations. But just as with alpha, A is the same on both sides of the mirror, and so they cancel out in their effect on X as well. And so what you find for the radiation pressure noise is basically a term that looks like this. It's just the sum of the B's times a factor out front, which represents the amplitude of the radiation pressure due to the coherent state acting on the mirror. But an important thing to notice about this is that if you do everything carefully, is that there's a B sub mu and a B dagger of minus sub mu that comes into this term, and that's going to be extremely important. Notice that we neglect the terms that go as e to the twice I omega naught times t. Those are fluctuations at 10 to the 15 hertz, and the mirror simply doesn't respond to fluctuations at 10 to the 15 hertz. So we can just throw those terms away and not look at them because of the extremely high frequency in the of the light in the laser beam that's shone on them. If we look at the motion now of the of X, let's assume that X is freely supported. Its actual frequency is down around 1 to 2 hertz. So the approximation that the mirrors are just free particles rather than harmonically trapped at 1 or 2 hertz is a reasonable approximation. That's equal to the force on it. And the radiation pressure force is then proportional to alpha, the coherent state amplitude, times these vacuum fluctuations due to the stuff coming into the output port. At frequency nu, this is a combination of B sub mu and B dagger of minus nu. When you solve this for X sub mu, we notice that the radiation pressure noise goes as nu to the minus 3/2. There's a 1 over the square root of nu to normalize the X's. These are supposed to be the annihilation operators for the position of the oscillator. And the output from the X motion, therefore looks like, at the output port, looks like B sub mu. That's going to eventually produce the shot noise. Times term alpha, the coherent amplitude of the laser beam, divided by m, times nu to the minus 3/2. This is the radiation pressure noise. And the important thing to notice about this is twofold. Number one, this has an I in it. So this is opposite phase of this. And the second thing is that this is a combination of the annihilation operator and a creation operator. This whole thing looks exactly like an annihilation operator for a squeeze state. So this is a squeezing, what we find is that the mirror is acting as a squeezing operator on the light that is coming into the interferometer. Notice that if we make the mass larger, it reduces the radiation pressure noise, as does putting in a higher laser frequency. Notice that the noise drops as nu to the minus 3/2. So the radiation pressure noise is important only at low frequencies, which is what we saw in that earlier graph that I looked at. Also, the laser amplitude, as we crank up the laser amplitude, that increases, as you would expect, the radiation pressure noise on the mirrors as well, but it doesn't change the shot noise. But as I said, the most important thing is that the output is a squeeze state. The output I'm just repeating this. But this is important because what it says is that if we feed into B, not the vacuum state, but we feed in a squeeze state, a state which is squeezed in the opposite direction to this squeezing that the mirror produces. It's going to be a frequency-dependent squeezing because as nu becomes large, this term becomes unimportant and the squeezing disappears. So the squeezing is going to be, thank you. The squeezing is going to be, if one puts in the opposite squeezing, one can cancel out basically both of these, convert them into the same thing so that one gets simply an annihilation operator acting on that squeeze state coming in. One can then, since the actual signal coming out is the real part of this whole thing, one can also decrease the noise coming out the output by doing a uniform squeezing on all of the radiation that's coming into the system. Now, this is all sort of conventional theory, and I'm assuming that the harmonic oscillator is a quantum system. The position, the free motion of the particle is a quantum system. What if it's classical? What if big things like 40-kilogram objects are really classical, as many people have hypothesized in the past? What will happen then? Well, the first thing is that X is now going to be a C number. It is not going to be a quantum object, because that's what I'm assuming, that this is just a classical system. Similarly, the force on the oscillator, the radiation pressure noise, which comes about from the quantum mechanics of the light, has also got to be a classical kind of noise. Now, the model I'm looking at is completely linear. I'm assuming all the nonlinear terms are negligible. And so they're all Gaussian states. So what I can do is I can replace the force on the oscillator, the radiation pressure source, which is a quantum source, by a classical source, which has the same expectation value and the same variance as the quantum one does, but now it's a classical one. So instead of operators B and C affecting the position of the oscillator, I'm going to assume that these are amplitudes B and C, which are classical amplitudes. What I get then in the output is a quantum operator plus a classical operator. That's not a squeeze state. That's simply a displaced state. It's displaced by a random variable, but that doesn't matter. It's just simply a displaced vacuum state. And in particular, one cannot cancel out the effect of the radiation pressure noise by doing a squeezing on the input from the input into the dark port. At best, one can reduce the shot noise by feeding in a squeeze state into the output port. This is just classical, which I can't reduce by putting in a squeezing operator. In fact, the squeezing operator will increase this instead of decreasing it. So the two noise sources, the shot noise and the radiation pressure noise, are no longer things that can interfere with each other as they do in a squeeze state. They're independent noise sources acting on the system. And as a result, one cannot do it, one cannot get rid of that by the squeezing operation. And there are, in fact, at least preliminary indications that squeezing of the input, doing variable squeezing of the input, works. In particular, there was a paper published 2 years ago in Nature Physics, actually in Nature, which makes this argument This is the title of that paper, in which they actually shone laser light and put in squeeze states into the input port, and those squeeze states rotated as a function of the frequency. And that rotation, in fact, did reduce the noise source, both from the radiation pressure noise and from the shot noise at the same time. So that suggests strongly that those mirrors are really acting like quantum objects, not like classical objects. Remember, this is 40 kilograms. This is more than you're allowed to take on the airplane in your suitcase without paying extra money. These are very, very, very macroscopic objects. Of course, their motion is very microscopic. They're only moving of the order of 10 to the minus 18 meters due to these radiation pressure fluctuations and so forth. But they're definitely classical objects. So people's attempts to produce quantum mechanics, which is quantum down below and classical up here, that we are really classical beings rather than quantum beings, I think does not accord with the way in which LIGO works. Now, there are broader applications of these ideas, which I obviously am not going to be able to cover. For example, the quantum microphone that the group of us suggested for use in the Bose-Einstein condensates in order to measure the fluctuations of the Bose-Einstein condensates as a single point in the Bose-Einstein condensate, rather than destroying the Bose-Einstein condensate every time that you want to see the pressure fluctuations, as is usually done. One can actually stick this little laser interferometer quantum microphone into the BEC by shining laser light, 2 frequencies of laser light through the BEC, and measuring the fluctuations due to that. It's actually an interferometer. I'll finish at this point. It's actually an interferometer, just like LIGO is, and a lot of the motions from LIGO can be applied directly there. So I will just page through that to show you that it's there and quit. Thank you.
Okay. Thank you a lot for your presentation.
I should stop sharing.
Okay, maybe the questions ask about the presentation, but go ahead, Cisco.
Thank you. Also, thanks, Bill, for sharing. That was really good. I'm curious, is there absolutely no way to correlate the 2 noise sources classically from like a common intermediate third party, maybe?
One's a quantum operator and one's a classical operator. What you're trying to measure is B plus B dagger. Now that capital B plus little b, or little b plus B star, which is just a classical real variable. It is a random variable, but on every time you run this whole system, that random variable has some value, and it just sticks at that variable. So the answer is no, that the 2 don't they don't interfere. It's basically the interference, and as we know, interference of a classical particle is one of the primary things that's quantum about it. And it's that interference between the B plus B with if you will, the momentum plus the position that is giving you the noise reduction by the squeezing. And you can't have that noise reduction by the squeezing in this case.
Okay, thank you.
In fact, if you try to squeeze it, we know that if you try to squeeze it, let's say at 45-degree angles, if excuse me, if the shot noise and the radiation pressure noise are almost of the same amplitude, Then if you squeeze it, you're squeezing it on a diagonal, and it makes the fluctuations on both X and P much worse. It makes the fluctuations on X plus P, if it's a quantum system, better. But if one is a classical and one is a quantum, it makes both of them much worse. And so it would make the noise much bigger rather than much smaller. So the crucial thing in LIGO is that interference between the radiation pressure noise and the shot noise, etc.
So sorry, we are like now the end of the time. So we'll be moving for the next questions. But before we'll thank Bill again.
Oh, now I can actually turn on my video.
Okay, it would be nice. Great.
Hands are popping up all over.
Yeah.
I think Masahiro was first, but hi,
Yes.
Masahiro.
So now questions are open for all speakers of this afternoon. They can answer your questions. So yeah.
Why don't we
Great.
take Masahiro first, because he had his hand up first.
Yeah, that would be great.
All the hands have disappeared again, but
Yeah. I have a question. So in the last slide, you comment about the quantum microphone, which explained the Bose-Einstein condensation.
right.
But I'd like to know the size of the Bose-Einstein condensation. So what?
So the Bose-Einstein condensation that we're thinking of is about 1/10 of a millimeter across and about 1 micron thick. So it's a circular plate just sitting there in a trap.
So that is a very smaller than compared to the mirror in LIGO experiment, right?
Certainly, it's much smaller.
So it should be quantum.
It also differs from the LIGO experiment in that in the LIGO experiment, the system was probing these 40-kilogram mirrors. Here, you're looking at the sound waves in the Bose-Einstein condensate, this tiny sound waves in the Bose-Einstein condensate. So they are definitely quantum. But it turns out that this particular kind of microphone, if you will, has a very interesting feature in that it doesn't damp out the fluctuations in the Bose-Einstein condensate. The two frequencies, the above and the below frequency for, at the laser, turn out one amplifies and the other one de-amplifies in such a way that they exactly cancel each other, so that one gets a microphone which doesn't alter the sound waves. It adds some noise into the sound, but it doesn't alter the sound waves themselves at all, which is a really nice feature. And if those sound waves propagate away from the microphone, then they don't bother the microphone again. Of course, in a Bose-Einstein condensate of a small size, they're going to hit the boundaries and bounce back, and you will get a bit of a mess. So I'm constantly telling Jörg Schmidtmeyer that he's supposed to make me a Bose-Einstein condensate that instead of 1/10 of a millimeter in size is 1 meter in size. In which case, since the velocity of sound in the Bose-Einstein condensate is millimeters per second, it's going to take hours for the sound to get out to the boundaries and bounce back in, at which point one will have finished doing the experiment. For some reason, he seems to be resistant to building me that kind of a Bose-Einstein condensate.
Oh, interesting. Thank you very much.
So now, if anyone has questions for any of the speakers of this afternoon, please raise your hands and we can go over it. So Igor, go ahead.
Yes, hi, can you hear me?
Hi.
Yes.
Okay, great. I had to switch on my microphone. Just a second, I tried the video as well. Okay, hi. Yes, I got my group here as well. Yeah, thank you so much, Bill, for a really interesting talk. Just to follow up on your last question in terms of the size of the BC, if that's a limitation currently for getting the right sound waves, could you instead look at a superfluid helium, where in principle you could get much larger sizes and maybe similar effects there?
Right. One of the big problems with superfluid helium is that if you look at the sound waves, they travel at about 300 meters per second. And as a result, you know, in order to get that 1 hour, this superfluid helium thing would have to be many kilometers in size. And for some reason, people have difficulty with that as well. Now there's a group, the Nottingham group, in fact, is trying to build one in which they're looking at the surface waves on liquid helium, which travel much, much more slowly, especially with the very shallow depths that they have. So it looks much more like the Bose-Einstein condensate. One of the problems there is that you have this laser shining through through the liquid. And the way in which in the Bose-Einstein condensate we got around that was by having two laser beams, one above the resonant frequency and one below the resonant frequency. And their effects basically cancel out on the Bose-Einstein condensate. In liquid helium, the resonances are way up in the ultraviolet. And finding good ultraviolet lasers is almost as hard as finding a 1 meter in size Bose-Einstein condensate, it seems. So that trick doesn't work as well, and that makes the experiment much more difficult. And the microphone then affects the system much more than one would like. But that's being actively pursued, and you know there's a good possibility that we'll figure out a way of making that work as well. And that, as you say, would be much nicer in the sense that it's larger, and the surface waves also travel very, very slowly with a thin enough layer of liquid helium. So you can get its velocity of sound, its velocity of the surface waves down to millimeters per second as well. Just as you have for the Bose-Einstein condensate. So yes, that's a very important observation.
So, thank you. Is there, like, there was before a hand, but do you still want to ask a question, Cisco?
I was just going to chime in, but Bill explained exactly what I was going to point out. So,
okay, perfect. So, are there any more questions for any of the speakers of this afternoon session, like just some of the ones that were before? So, if no more questions are asked, we can wrap up this session. And if some questions were left, you can ask them on Slack to the speakers. And with this, I want to thank you all for coming, and we finish this session today.